Hi, I'm Reena. In this talk, I'll be presenting GAPP, a profiler for detecting serialization bottlenecks in parallel Linux applications. This is a joint work with my supervisor Tony Field at Imperial College London. Serialization bottlenecks cause parallel tasks in an application to execute serially, thereby limiting their performance. These bottlenecks are caused either due to contention for resources, where it can be hardware resources such as CPU, peripherals, etc., or software resources such as locks. Load imbalance among threads can also serialize the execution, as in the case where threads wait on barriers or where threads execute different tasks in a pipelined fashion. Whatever the reason, serialization bottlenecks are characterized by reduced parallelism. As you can see, tasks exhibit maximum overlap when there is no dependency, while they exhibit long waiting periods when there is dependency between them. Developers rely on profilers to identify the reason behind poor performance of their applications. However, profiling tools tend to focus on issues triggered by a specific class of resource, but applications may experience a combination of these bottlenecks, some of which are architecture specific. We present GAPP, a lightweight profiler that can identify several different types of serialization bottlenecks. It doesn't require applications to be instrumented and has been validated on both multi-threaded and multiprocess applications in C or C++. It is implemented using extended Berkeley packet filter, which provides fast and secure kernel tracing. The next few slides will discuss the underlying design principle of GAPP. The main principle that drives GAPP is to harness the symptom of serialization bottlenecks. As we have seen, thread serialization is characterized by reduced parallelism. So, we need to identify when and where reduced parallelism is exhibited. We consider reduced parallelism as when the number of active threads is less than or equal to nmin, a tunable threshold variable. The default value of nmin is set to half the total number of threads in the application. The number of active threads can be maintained by probing context switch events and incrementing the count when threads are switched in and decrementing it when threads are blocked. With this logic, the number of active threads during each interval is displayed at the bottom in green. The same prob can retrieve stack traces at the end of a time slice to identify code location that executed with reduced parallelism. The overhead in retrieving stack traces can be further reduced by limiting stack trace retrieval to critical time slices alone, that is, time slices whose average active thread count is below nmin. This will filter out time slices with short spells of reduced parallelism. Subsequently, in the example shown, we will end up with only one stack trace st3 as the only critical time slice is that of thread 3. This will work fine if the bottleneck code happened to execute at the end of a time slice, but this cannot be guaranteed every time. For example, as observed here, thread 2 exhibits reduced parallelism before the next stack trace retrieval opportunity. This limitation can be overcome by periodically sampling the instruction pointer and processing them only if it represents a critical code. For example, IP6, IP7 and IP11 are rejected since the number of active threads is greater than nmin at that instance. In this figure, all time slices are critical and hence stack traces will be retrieved at the end of each of them. The instruction pointers can be combined with stack traces, which will together provide information regarding the bottleneck code and the call path that led to it. Moreover, each time slice is assigned a metric which considers its duration and degree of parallelism. This metric, named CMetric, distinguishes threads that execute for short periods with low parallelism from those that execute for longer periods with a similar low degree of parallelism. Now that we have the bottleneck codes and paths that led to it for each critical time slice, similar call paths, their instruction pointers, and CMetric are combined and sorted to generate critical call paths, bottleneck functions, and lines of code. The tool also displays the CMetric for all threads in the application. Details of how this is achieved is given in the paper. The critical paths and functions provide us information about possible optimization opportunities in the application. Similarly, non-uniform CMetric indicates load imbalance among threads. In the next few slides, we will explain how we have evaluated GAPP by experimenting with applications from the Parsec 3 benchmark suite and two large open source projects, MySQL and Nektar++. All applications except Nektar++ are multi-threaded. Nektar++ implements parallelism using MPI primitives. We will see how GAPP identified load imbalance among threads in a multi-threaded task parallel application, Ferret. The application is designed with 6 pipeline stages, the first and last being serial phases. It was tested with equal number of threads in all parallel stages. The top critical path identified by GAPP pointed to functions from the ranking phase, and threads in this phase exhibited higher CMetric when compared to others. As observed in the graph, threads in the last phase exhibited higher CMetric than others. We reallocated threads between stages until we got a uniform CMetric value for all the threads. This eventually reduced the execution time by almost 50%. GAPP was also able to identify cases of resource contention in MySQL when tested with the OLTP read-write workload from Sysbench benchmark. The top two critical paths were related to disk I/O and spin wait loops respectively. The disk I/O was a bottleneck because of limited buffer size. Increasing the buffer size improved transaction rate by 19% and reduced latency by 16%. The second bottleneck was a custom-built spin lock that blocks after spinning for a predefined time. Suspecting frequent cache invalidation a possible cause behind this bottleneck, we increased spin wait time, which reduced cache misses by more than 10%. Moreover, these two modifications cumulatively improved query transaction rate by 34% and reduced average latency by 25% for the same workload. Even though these issues can be identified by MySQL performance tuning tools, the experiments show that GAPP, which is a generic tool, is capable of identifying similar architecture-dependent bottlenecks. Next, we will see how GAPP was used to optimize BodyTrack, a multi-threaded application that follows producer-consumer paradigm. GAPP identified a function in the producer's main loop, output BMP, as a bottleneck function. While the producer thread is executing this function, the workers or consumers are waiting on a conditional variable. Offloading this function to a separate writer thread improved performance by 22%. We also experimented GAPP with an MPI-based PDE solver, Nektar++. The results obtained by GAPP for Nektar++ can also be obtained with MPI profiling tools. GAPP identified load imbalance among the MPI processes, which was caused by non-uniform mesh partitioning in the solver. The critical function identified, DGEMV, was a matrix multiplication routine exported by the BLAS library. We replaced the default BLAS library with OpenBLAS, and this improved runtime by 27% and shifted the bottleneck to a different function. conclude, we were able to use GAPP to identify different types of serialization bottlenecks in different classes of applications. The results generated by GAPP were observed to be consistent across multiple runs under the same test condition. GAPP is designed to be customizable with tunable parameters nmin, sampling frequency, stack depth, option to include results from dynamic libraries, etc. Still, it has got the limitation that it will not work with spin weight loops, which doesn't block. You can download GAPP from GitHub, and the GitHub page also discusses GAPP's sensitivity to the various tunable parameters. That's all for now. Thank you.